Okay, so maybe we should get started. I see some of you don't, well, I don't see some of you don't like mornings. So it's too bad, I guess. The videos are being uploaded right now from previous lectures, which will be too, so I guess people who are not here can catch up there. So last time we discussed some statements about structure and universe as a whole. We first of all discussed that the night sky is dark, and then we discussed that the reason why the night sky is dark is largely because the age of the universe is finite. And then we discussed how we might study the universe as a whole, and we noted that two properties are going to be essential for our purposes: homogeneity and isotropy. So the equations we'll write down will apply on the scales at which homogeneity and isotropy are operating. So scales bigger than 100 megaparsecs. So we're going to talk about the expansion of the universe. We're really talking about the expansion of the universe on scales bigger than 100 megaparsecs. So someone asked me last time at the end of the lecture whether the expansion of the universe meant that atoms were getting bigger. The answer is no. The Bohr radius of an atom remains the same size and has remained the same size at the beginning of the universe. The statements about the expansion are really large-scale statements, not statements about everything. Okay? So things that are gravitationally bound will not be, expanding away from each other when things start to fall out of the horizon. So things which are gravitationally bound stay together, and this puts an upper limit on things like complexity in the universe. Okay, then we concluded with a statement of Hubble's law. And Hubble's law is the empirical observation that if you look at the velocity of galaxies, this velocity follows a linear relationship with the distance to the galaxy. So today, we'll start by saying more about the Hubble law. Last week, we talked about the Scalar model of particle physics briefly, but not all the Scalar model of particles are relevant to cosmology. So we'll focus on the species that are going to be of importance to us later in the class. We'll say a few words about them. One particular thing of interest is the photon, light, and we'll discuss the background radiation bath in which the universe lives. And we'll see there's a relationship between the temperature of the universe and the size of the universe. So we'll derive that relationship today. Okay, so before we get moving, any questions? Okay, so in stating Hubble's law, we've noticed there's a relationship between velocity and distance. So we need to explain how to measure these things. So the way you measure distance is you know how bright something is intrinsically, and you see how bright it looks, and you figure out how far away it is. So if you had a light bulb, for example, which you knew exactly how bright it was, if you moved it further and further away, you know the flux from the light bulb falls off as the inverse square of the distance. So by looking at how bright it looks to be, you can figure out how far away your light source is. That's essentially what you do with certain scanning stars. You figure out what their intrinsic brightness is, look at their apparent brightness, and by looking at the difference between the apparent brightness and the intrinsic brightness at a fixed distance that you know, then you're able to figure out what distance the object is. Velocity is a bit trickier. We'll look at the wavelength of light. So we know in the laboratory that the wavelength is lambda emission, and we measure this using absorption lines in a lab. And then we measure this for a distant galaxy, and lambda observed will turn out not to equal lambda emitted. So you can use this relationship to compute a factor called the redshift. So the redshift is basically a statement of the Doppler effect. So if you were listening to a train as it's approaching you and a train as it's passing you, the frequency will change for the sound the train makes. The same thing applies to wavelengths of light, and you can use this to determine redshift and blue shift. So redshift is defined as lambda observed minus lambda emission divided by lambda emission. So the redshift is negative, which means that lambda observed is smaller than lambda emitted. This is called blue shift. It means an object is moving towards you. And if z is positive, it's called redshift, and the object is moving away from it. So by measuring the blue shift and the red shift, we notice that most galaxies are moving away. The closest galaxies, like the members of the local group, for example, the closest galaxy to us are the magnetic clouds, they're moving around the Milky Way. And the Milky Way is moving towards Andromeda, so these are the two biggest galaxies in the local group. So, past couple of days, there were some research papers published about how there was another companion galaxy in the local group that Andromeda cannibalized. Andromeda is a big galaxy, and it ate up a galaxy comparable to the size of the Milky Way. That may be the fate of our galaxy when it approaches Andromeda. Moving towards each other, it should be about 4 billion years from now. So galaxies that are close to us, they moving towards us or around us. So these redshift formula really apply to galaxies that are a bit more distant than our nearest neighbors. So Hubble moved the redshift for about 50 galaxies. So this was the mid-1920s. And based on this, he plotted redshift versus the distance, and he noticed there was a linear relationship. The empirical relationship is h naught r over c. So z, the redshift, is, so the relativistic expression of the redshift is this expression here. And this is about v over c. So you together expand it, you get this expression here. So z is itself approximately v over c. So plugging this in, we get v over c is h0 r over c, or v is h0 r. So Hubble had a not so good initial measurement of h0. The modern measurement is about 70. But as we mentioned last time, different ways of measuring h0 give slightly different values. And because the units of h0 are inverse time, this is related to the age of the universe. Since the age of the universe will go like h0 inverse. Okay, so the conclusion is the galaxies are moving away from us. And there are two explanations for this. One explanation is that we're the center of the universe and things are just moving away from us. The other explanation is that if you're at some other galaxy and you also measure the Hubble law, you see the same Hubble law we do. So things are moving away in general. consistent with cosmological principle is the second explanation we prefer, that everything is moving away from everything else. So if we think about different galaxies, so let's look at this sort of system. We have 1, 2, 3. This is the vector R12, the vector R23, and the vector R31. Rij is the length of Ri minus Rj. So if we're in galaxy 1, we're seeing galaxies 2 and 3 moving away from us in accordance with this equation. So we can write for a homogeneous uniform expansion R12 Rij as a function of t as being A as a function of t times Rij at a time t0, a reference time t0. So t0 is today. So this A of t basically describes the expansion of the universe, so it's called the scale factor. And we normalize A of t so that A of t0 is 1 today. So the scale factor was smaller in the past since the universe is expanding. So the statement is that Vij of t is a velocity, so the time derivative of the distance. This is a dot of t, Rij of t0. So we can write this expression then as a dot of t over A of t, Rij of t. Just multiplying and dividing by A of t. Comparing this relation to the Hubble law, we have Vij of t is a dot of t over A of t, Rij of t. So this tells us that there's a function h of t, which is a dot of t over A of t. So this is h of t, Rij of t. And today, h of t0 is the velocity, well, this is the expansion of the universe at time t0. So this is a of t0 is equal to 1 in our normalization. So this is the expression of h of t0. But in general, at some other arbitrary time, h of t, we give the ratio between the change in the scale factor and the scale factor to define this Hubble function. So the Hubble parameter, h0, is h of t0. People will often say this is the Hubble constant, but it's really a function of time. Okay. So the claim is that an observer in galaxy 2 or galaxy 3 has the same velocity-distance relationship. So V is HR for any observer and h is a dot over a. So in galaxy 1, we're seeing 2 and 3 move away from each other. So the picture we have is a triangle is getting bigger in time. But with respect to galaxy 2 and galaxy 3, the triangle is also getting bigger in time. So 1 and 3 are moving away from 2, and 1 and 2 are moving away from 3, just as 2 and 3 are moving away from 1. So for any observer in any galaxy, we measure the same Hubble law. Okay, so I just erased the formula for the redshift, the relativistic formula. Let me just make a few comments about this. One is you need to be careful about using the full relativistic formula. So the reason you have to be careful is that light doesn't propagate instantly. So light takes time to propagate, and during the time in which light propagates from a distant galaxy to us, the relative velocity of objects may have changed slightly. Okay. So you need to have some exercise of caution in using using this formula for Z for Lorentz velocities. Okay. Cool. Okay, so if galaxies are moving apart today, that means in the past that we were closer together. So, with no forces to accelerate or decelerate, which is a questionable assumption which turns out to be wrong, but let's just go with it for the moment. The time is of order r over v. We take a distance and a velocity, that's a natural ratio you have in order to figure out some time scale by dimensional analysis. So this is r h0 over r, which is 1 over h0. So the Hubble time is the inverse of h0, and this works out to about 14 billion years, which is our first guess for the age of the universe. It turns out not to be a bad guess, since the universe is about 13.8 billion years old. So, gravity, tendency of gravity is to bring things together. It's a force of attraction between masses in the universe. So gravity works to slow the expansion. And this means the universe will expand more rapidly in the past than it does in the present. So the universe is in fact a bit younger than h0 inverse. Okay, so these are statements that are made in a very naive sort of way. So when we're a bit more exact, we'll see that some of these statements, in fact, need to be modified. So there's a term in the Einstein equations called the cosmological constant. We usually write this as lambda. So this is a fudge factor Einstein introduced into the original equations in order to avoid an expanding universe. This fudge factor turns out to be important, and it turns out this is a dominant effect in describing the evolution of the scale factor today. It turns out that while gravity is working to slow the expansion, the effect of the cosmological constant is to enhance the rate of expansion. So it turns out that the change in the scale factor is such that the universe is expanding faster and faster and faster today. So the universe is accelerating its expansion because the cosmological constant term is acting like an anti-gravity effect. Okay? And we'll see what that means later on. So the realization that the universe is accelerating in its expansion, that was only made in the late 1990s. So I was in graduate school at the time. And I remember hearing lectures on this when people first found this out. So this is a recent development that this cosmological constant term came back. So up until the late 90s, when this term had to be taken into consideration, we all thought lambda was equal to 0. And the reason we thought lambda is equal to 0 is because the universe is expanding, we don't need lambda, so why wouldn't it be very close to 0? And we thought that there was some symmetry principle that enforced the fact that lambda equals 0. That turns out not to be the case. Lambda is small, but it's positive, and is driving the expansion of the universe. It's the engine for the acceleration of the expansion of the universe. It's still confusing what lambda actually is. So one of the consistent problems people encounter in quantum gravity or cosmology or whatever is that we don't know what lambda is. We call it dark energy sometimes, but that's just a name to hide our confusion. We don't know what it is. Okay. So we learned something. We learned the universe is expanding based on Hubble's observations. And let's revisit Olber's paradox, given what we've learned. So T0 is approximately H0 inverse, and the number density times the average luminosity is 2 times 10 to the 8 solar luminosities per megaparsec cubed. So the flux due to galaxies, total flux, is 4 pi J galaxy, which is NL integral 0 C H0 inverse dr, which is NL C over H0. So this is 10 to the minus 11 solar luminosities per square astronomical unit. And the sun is 1 solar luminosity per 4 pi astronomical unit squared, which is about 0.8 solar luminosities per AU to the minus 2. So the flux from the galaxies compared to the flux from the sun is about 10 to the minus 10. So this explains when the night sky is dark, because the universe has a finite edge. So Hubble's law is a natural consequence of the Big Bang. So we can think about this expansion of space as a consequence of there being some initial singularity from which the universe was born, and the expansion has been happening ever since the Big Bang. So the alternative to this is a steady-state universe where we have a more perfect cosmological principle. We say that instead of everywhere in space and everywhere we look, so each direction is the same, each location is the same, the steady-state universe is each time is the same as well, and that requires matter to be constantly created. And we can think about the universe in a steady-state universe setting as being infinitely old, but the observations of the cosmic microwave background means that the Big Bang model for the universe went out over the steady-state model. So let's see how that works. So first, Hubble's law is natural in a Big Bang cosmology. But there is an alternative. Steady-state universe, which uses a perfect cosmological principle. But there's no privileged time. So, dr dt is proportional. The velocity is h0r. So we can write this as r of t. We're just integrating this expression. We write this as, well, let's do the integral. We have dr over r is h0 dt, which tells us the logarithm of r is h0t, also constant, which tells us that r is r0 e to h0t. Okay? So I just integrated. So r goes to 0 in the limit where t goes to minus infinity. So the universe is infinitely old in the steady state setting. So the volume of the universe is 4/3 pi r cubed, which is proportional to e to 3 h0t. So just cubing this, I'm ignoring factors of 4 pi and r0 and so on. So the density must be constant for steady state, since there's no privileged time. So the mass of the steady state universe, the change in the mass, is rho 0, the density today, times the change in the volume. And this is rho 0, 3 h0 times the volume. And the density today, where the cosmological principle applies, is 3 times 10 to the minus 27 kilogram per meter cubed. So M steady state over the volume, change in that is 3H0 rho 0, which is 6 times 10 to the minus 28 kilogram per meter cubed per billion years. So roughly, in order to maintain a steady state universe, this translates to 1 hydrogen atom per cubic kilometer per year just suddenly appearing. So this is so small a rate of creation of matter, it's not something you'll ever observe. Okay? So this is just tiny, 1 atom per cubic kilometer per year. So even if you create a perfect or a near perfect vacuum, there's still going to be some particles sitting around. You create a perfect or near perfect vacuum of the size of a cubic kilometer, and then just watch it for a year and count the number of particles and see that the number of particles increases by 1 atom. Good luck with that experiment. The steady state universe says the universe is the same at any time, so the temperature of the universe isn't really changing as a function of time. So the reason the Big Bang won out is we measured this cosmic microwave background. It indicates the temperature changes as a function of scale. Okay? So that's why measurement of the CMB in detail means the steady state universe goes away. And we'll see what that means later on. Okay? Is everyone happy with Hubble's law? So we'll move on. Okay, so we discussed the standard model. So as of April this year, the standard model has been tested in certain contexts with 13 decimal places. So you do an observation of what's called the fine structure constant, and you do a calculation of what the fine structure constant should be. The theoretical errors are because of an incomplete understanding of a theory called QCD, quantum thermodynamics, that to the accuracy of 13 decimal places, the theoretical computation matches the experimental result. So this is there's no better comparison between theory and experiment anywhere else in science. Even things like the inverse square law, the 1 over r squared, that too has not been measured at 13 decimal places. So this is in fact a great corroboration of quantum field theory. So in the standard model, particles come in 3 generations. There are 6 quarks, up and down, charm and strange, top and bottom. There are 6 leptons, the electron, muon, the tau. In each of these electron, muon, and tau comes with a neutrino. And in addition, there are particles, the photon, the W plus and W minus and Z vector bosons, and the Higgs, which tell us how these particles interact. It turns out, however, that for most practical purposes, only the particles in the lightest generation will matter. So the proton you can think of as being an up quark, a down quark, and these particles are held together by gluons. So the proton is up, up, down. The neutron is up, down, down. Just held together by these gluons. And these are basically the only quarks and gluons is a theory called QCD, quantum chromodynamics. And QCD tells us that there's a phenomenon which we don't understand fully, called confinement. So in QCD, the quarks and gluons come in colors. So colors are a colorful way of expressing the idea that these things transform in what are called representations of a gauge group called sp3. Details are not relevant here. But the idea is that at low energies, because of confinement, we don't see individual quarks. We see downstates of quarks. The two downstates that we encounter are the proton and the neutron. And the periodic table is constructed out of atoms whose nuclei are built out of protons and neutrons. Okay? Protons and neutrons, however, are not fundamental particles. They have substructure. The substructure are these quarks and gluons. In addition to the protons and the neutrons, in order to build atoms, we need electrons. So electrons are fundamental particles. And we also need neutrinos. The neutrinos come in three species. And because all these species are very light, all three species become important in cosmology. In addition to electrons and neutrinos, we've got these other massless particles. So the gluons are massless, but the gluons come confined in these protons and neutrons. So we don't see free gluons either. We do see free photons. So this is just light. If you like, it's the potential associated to electromagnetism. So these photons are also relevant to cosmology. The final thing that we care about is not in the Standard Model, so I don't really know how to describe it yet, but it's called dark matter. So what is it? Good question, I don't know, but it's important. Okay, so in the parlance of cosmologists, anything which is moving relativistically is called radiation. The neutrinos are very, very light particles. They do have mass, but they move very close to the speed of light. So we classify neutrinos and photons as radiation. Everything else, the protons, the neutrons, and the electrons will classify as matter, and also the dark matter is matter. So by matter, we just mean stuff that has a gravitational response that doesn't move relativistically. Okay. So the matter, it'll turn out, is roughly is roughly 30% of the universe. The radiation is roughly 8.4 times 10 to the minus 3%, and the cosmological constant which is our best candidate for this so-called dark energy, that's 70%. So of the matter, 4% is what we call visible, and 26% is dark. So everything you see in the cosmos is stuff related to, the matter. So this matter here, stuff built out of protons, neutrons, electrons, those constitute the stars. Those constitute all the galactic clouds. Those are the things that shine. Those are the things we can observe visibly in our telescopes. That's only 4% of what's there. So that means that 96% of the universe simply doesn't care about it. So this cosmological constant, dark energy, is sometimes also called the vacuum energy density. So all these are synonyms for this stuff we don't understand. So the development of quantum mechanics historically traces to certain confusions that people started to develop in the mid-19th century. So thermodynamics was invented in the mid-19th century. And in thermodynamics, it was noted that there were things called black bodies. Black bodies have a property that suppose we have some object of a random shape, and we heat this up to a temperature T, and we have a small opening through which light can come out. That light will follow a distribution which is a function only of T. So in particular, the shape of your oven does not matter. The light that comes out of your oven is independent of how it looks. So the spectrum of black body photons, so this is the energy density in the photons as a function of the frequency. This is 8 pi h over c cubed, nu cubed, d nu, e to the h nu over kBt minus 1. So let's just look at this formula briefly. We know that h nu over k, so h nu is an energy. This is Planck's equation for the energy as a function of frequency. We also know that kBt is an energy. So it makes sense that h nu over kBt is a dimensionless quantity, dividing energy by energy. So this is a natural thing to appear in this equation. So we have this dimensionless quantity that's apparent here. The units of h over c cubed, so nu is a frequency, so it's 1 over time. d nu is also a frequency, so you've got 1 over time squared. It's appearing in the numerator here. So in order to get, so this is energy density, so this is energy per volume times a time, an inverse time. So this is, sorry, this is 1 over time to the 4th. So nu is hertz, it's per time. d nu is also hertz, so it's 1 over time to the 4th. So in order to get units of 1 over time to the 4th, we need this combination h over c cubed in front. So h is is basically, so you're looking at this, H is energy per, so it's energy times time in order to kill the 1 over time from the nu. So if you look at, so this is here, energy times time, and then C cubed is length divided by time cubed, and then we said that nu cubed over d nu to the 1 over time to the 4th. So you work all these units out, you'll find units on the two sides of the equation. Okay? In any case, that's the formula for black body spectrum. If you plot that formula, energy density versus frequency, you'll find that the curve looks so. Okay, so first we'll notice that there's a maximum for the curve, and this is going to be characteristic of the temperature. It works out to 2.82 kV/T. If you integrate over all frequencies, epsilon radiation is the integral of d nu, epsilon of nu, from 0 to infinity. And this works out to alpha t to the 4th, where alpha is pi squared over 15, a Boltzmann to the 4th, h bar cubed c. And this is 7.56 times 10 to the minus 16 kilogram per meter second squared Kelvin to the 4th. So that's the energy density of the radiation. The number density of the radiation is going to be the energy density of the radiation divided by h nu, which is the energy of a single of a photon with this frequency. So if you integrate similarly, so this is n, so this is, call it n of nu d nu, is that. If you integrate n gamma as the interval from 0 to infinity d nu, n of nu, this works out to beta d cubed, where beta is 2.404 over pi squared, ab cubed, h bar cubed, c cubed. And this is 2.03 times 10 to the 7th per meter cubed Kelvin cubed. Okay, so what I've done here is I've defined a number density as taking the energy density divided by the energy of the photon. Okay, so I've canceled units of energy, you get a number density here. So the mean energy is energy corresponding to the mean frequency, which is the energy density over the number density, and this works out to 2.70 kV/T. So if you plot as a function of frequency at a given temperature, this is just normalization, c cubed, h squared, h pi, k Boltzmann cubed, t cubed. times the energy density, this curve will look like this. So this is the so-called black body spectrum. As you shift the temperature, the peak of the curve moves, but the shape of the curve remains the same. So what it tells us is most of the radiation has energy which is near the peak. There are very few photons with energy which is nearly zero, and there are very few photons with large energy. Tail dies exponentially. So comments. Energy goes like h nu. There's an exponential tail in the distribution, but the photons in the tail are very energetic. So if you look, for example, at the sun, the temperature of the sun is 5,800 Kelvin, at least in the solar atmosphere. So the photons that are coming from the sun have a mean energy of 1.3 electron volts, which translates to a wavelength of 9 times 10 to the minus 7 and this, so meters. And this is in the near infrared. So here's a question for you. If the mean energy is in the near infrared, why is it that evolution selected visible wavelengths rather than near infrared wavelengths? Yeah.
Does the atmosphere not absorb a lot of infrared?
Sorry?
Doesn't the atmosphere absorb a lot of infrared?
No, that's not the reason. It does, but it's not the reason. So what contributes more to the mean? The more energetic things, right? The peak, however, is in the visible wavelengths. So we're selected to see the photons, which are here, where they're more numerous in number. But the mean is affected by the guys over here, which are energetic. So the shape of the curve is what sets the mean, but the peak is set by the temperature, and we selected the visible wavelengths because of that. Okay, we're halfway through. You guys want a break? Okay, let's take 10 minutes. Okay, so let's get started again. So, much of what we know about the universe today is acquired through our investigation of what's called the cosmic microwave background. So, the universe is sort of, it glows. It glows with temperature in the microwave frequencies, and it corresponds to the remnants of a hot Big Bang. So if you measure the temperature today in space, as dark and distant a space as you like, you'll find that the temperature is non-zero. Temperature you measure, the minimum temperature you can measure in the universe, outside of the laboratory where you cool things down even further, is 2.725 plus or minus 0.001 Kelvin. So this temperature has a energy density, 4.17 times 10 minus 14 joules per meter cubed. This is a black body temperature. Associated with black body temperature, we have some energy distribution, E of nu, and the total energy density of that distribution is this, with the number of photons being 4.11 times 10 to the 8th per meter cubed. The mean energy is 6.34 times 10 to the minus 4 electron volts. This is much too low in energy to photoionize an atom. So if you have some atom with an electron going around it, you won't be able to knock out the electron with an energy of a photon like this. And it's way too low to photodissociate a nucleus. So it's not going to tear apart a nucleus of an atom by ramming into that. But at some point in the past, if the temperature was higher, these energies would be strong enough to photoionize and photodissociate. And these processes are very important in the formation of elements in the first place. So essentially the concentration of hydrogen and helium and so on, this was determined in the first 3 minutes. The temperature was very, very high, and during that time the energy was high enough in order to play a role in these rare processes. The wavelength associated to this energy is 2 millimeters, and it's the microwave. Hence the name, cosmic microwave background. So it was detected by Penzias and Wilson. They're the ones who cleaned the bird droppings out of their instrument, which were confused by background hum they were detecting. And even with a clean telescope, they found the same background hum in all the directions. They discovered this cosmic microwave background observationally. They talked to their colleagues who said it was predicted as a remnant of the hot Big Bang, and this corroborated that model. And this cosmic microwave background was since investigated by experiments called COBE, the Cosmic Background Explorer, WMAP, the Wilkinson Microwave Anisotropy Probe, and SWAMP. So these were 3 satellite measurements, and the detailed measurements of these instruments are basically what tell us a lot about the large-scale structure of the universe and how we understand, for example, the relative densities of stuff I talked about previously. Matter being 30%, cosmological constant being 70%. These were determined basically by these instruments. So the most recent, so the COBE instrument was the early 90s. WMAP was the mid 2000s. And Planck was the early 2010s. So these instruments are really telling us things now. So this is what I mean when I say we're living in a golden age for cosmology. We're learning a lot about large-scale structure of the universe in very recent years. So even 15 years ago, this very class would be very different. We wouldn't know a lot of the stuff we're talking about. So this is what makes cosmology a very exciting subject, in my opinion. So this cosmic microwave background is as far back as we can see. This imprinted the sky when the universe was 380,000 years old. So Planck Alternative cosmologies start off by saying that there'd be light. It turns out that the universe wasn't originally transparent to radiation. The universe is very dense. So when light was traveling, it would bump into something. As a result, it wouldn't propagate very far before it interacted with matter. It was only when the universe is 38,000 years old, the universe became transparent to light. So the mean free path of light became long enough that it's very unlikely that it bumps into something. So prior to this age, you couldn't see very far because your light wouldn't travel very far before it interacted with something. Okay. So as far back as we can see, we see this cosmic microwave background, and we see it's got a temperature. The temperature is uniform wherever we look. So black body radiation has energy density. We notice that the energy density is alpha t to the fourth. And the volume of the universe, so this is the density, this energy per volume. The volume is changing with the scale factor. This is the same scale factor we encountered in Hubble's law. So I'll state a fact, which I won't prove, but we'll get to a derivation of this later in the course. The fact I'm going to use is the pressure of a photon gas, P, is 1/3 the energy density. Okay? So you can check the pressure is force per area. Energy density is energy per volume. You can check these two things have the same units. So, we'll use the first law of thermodynamics and see what this teaches us. The first law of thermodynamics is essentially a statement about the conservation of energy. It's nothing fancy. It basically says the heat flowing in and out of the system is dE plus P dV. So dQ is the heat flowing in or out of the system. dE is the change in internal energy. And PdV is pressure times the change of the volume. Okay, so the system we're studying is the universe as a whole. Because we're studying the universe as a whole, there's no heat flowing in or out of the universe as a whole. So, dQ is 0 for the universe as a whole. This tells us then that dE is minus P dV. Okay. So let's take this equation and let's divide by dt. So dE dt is minus P dV. So P is a function of T. Just like volume, energy are functions of T. So the energy is energy density times the volume, and the pressure is, so the energy density times the volume is alpha t to the fourth times the volume. The pressure is alpha over 3 p to the 4th. Because I'm using this fact, the pressure is 1/3 of the energy density. So we plug these statements in to the previous expression, the first law. So we have then that dE dt is alpha d by dt. Alpha is just a constant. P to the 4th times the volume, which is alpha 4p cubed dt times the volume plus p to the 4th dt. And this is supposed to equal minus p dt, which is minus 1/3 alpha p to the 4th dt. So let's separate out the terms involving dt dt, the terms involving dv dt on both sides of the equation. When we do this, we find that 4t cubed dt dt times the volume is minus 4/3 t to the 4th dv dt. Or rearranging terms, this is 1 over t dt dt is minus 1 over dv dv dt. So v is proportional to a cubed of t, since a is a scale factor, and we're looking at a volume. So minus 1/3, 1 over 3 v dv is minus 1 over 3a cubed times 3a squared dA dt, which is minus 1 over a dA dt. So then we have 1 over t dt dt is minus 1 over a dA dt. So let's iterate this. This tells us that d by dt log t is minus d by dt log a. Or t is proportional to a of t inverse. So this tells us, so we can write a formula then, temperature is the temperature today times a of t inverse. Okay? So this tells us the universe is expanding. So as the universe is expanding, a is getting bigger. So 1 over a is getting smaller. So t is getting smaller as the universe expands. So the universe is cooling down with its expansion. It's cooling down inversely proportional to its size. So when the universe was 380,000 years old, is when the universe first became transparent to radiation. This is when we started seeing the CNV. It was a factor of A of this time, we call this T star. A of T star was 1 over 1100. So it was 1100 times smaller than it is today, since the universe is expanding, and we defined A of T0 to be 1. So this means that when the light we were seeing in the cosmic microwave background was emitted, the universe was 1100 times hotter. So the temperature at T star is 1100 times the temperature today. So the universe, the early universe, was hot, and because it was smaller before, it was also dense compared to how it is now. So the history of the universe we can track by looking at the temperature of the universe. Okay. So we see the temperature is related to the scale factor. So if you have any questions on this calculation, please ask. This is the kind of thing we put on the exam for example. Okay? Okay, so this essentially covers what I wanted to say on the scale factor and how it relates to temperature. So the two take-home messages today are that we have velocity is related to the distance, and the measurement of the ratio between velocity and distance is given by change in the scale factor compared to the scale factor. So this is essentially the content of Hubble's law. Hubble's law today is that V equals H0R, but it was also true in the past with a different value of H. And the second thing we want to notice is the universe is immersed in a radiation bath with a given temperature, and the temperature of the universe is inversely proportional to the scale factor. So those are the two key observations that we made today. Any questions? Okay, so tomorrow we'll start going over the exercises in the tutorial, and then we'll proceed from there. Yeah?
Yeah, I was just wondering, will the universe eventually cool to like absolute zero?
As the expansion continues, the universe will continue to cool. Whether it will cool to absolute zero, I don't know. There are other things that are happening in the universe. For example, there are chemical processes in the universe as well. The so-called heat death of the universe is that the temperature will keep on decreasing, and eventually it's unclear what will happen. Because right now we don't know what protons are state. We've never seen a proton decay, but we don't know that we have theoretical reasons to think that if we have a certain structure in particle physics, then protons will be stable. But we have no evidence the structure really exists in nature. So far, no one's seen a proton decay. We have no proof that protons should be stable. They're very long-lived, so that's good. But if protons decay, that's a different endpoint for the universe than if protons don't decay.
Thanks.
Other questions? All right, see you tomorrow.